Introduction to Statistics, Chapter 9, Estimating the Value of a Parameter, Section 9.2, Estimating a Population Mean. Recall that a point estimate is the value of a statistic that estimates the value of a parameter. When a sample is drawn from a population, the point estimate for the population mean is x bar, where x bar is the mean of the sample. At this point, we will need to introduce you to the student's t-distribution. The t-distribution is different for different degrees of freedom. Degrees of freedom is equal to n minus 1. The t-distribution is centered at 0 and is symmetric about 0. The area under the curve is 1. The area under the curve to the right of 0 equals the area under the curve to the left of 0, which is 0.5. Sound very familiar to the normal curve so far. As t increases or decreases without bound, the graph approaches but never equals 0. The area in the tails of the t-distribution is a little greater than the area in the tails of the standard normal distribution because we are using s as an estimate for sigma, thereby introducing further variability into the t-statistic. As the sample size n increases, the density curve of t gets closer to the standard normal density curve. This result occurs because as the sample size increases, the values of s get closer to the value of sigma by the law of large numbers. In statistics, 30 is usually the cutoff. If a sample size is 30 or greater, then we assume it to be normal, and S is a good estimate for sigma. Now, here's what the table looks like. This is a t-distribution table. Across the top here, we have the area in the right tail. Area in the right tail is across the top. Now, degrees of freedom is down the left side. Okay, these are your degrees of freedom. Now, let's look at some problems. Okay. Using student's t-distribution table to find t-values. Find t-value if the area to the right of t is 0.05 and n equals 12. So first, degrees of freedom would be 12 minus 1, which equals 11. Now we go to the table. Okay, the first thing we want to do is find the area in the right tail. Well, the area in the right tail is 0.05. So I find 0.05 across the top. Okay, degrees of freedom is 11. I go down the left side, find 11. So now I have my area in the right tail, degrees of freedom. Now I find where this row and this column meet. That becomes my t-value. So in this case, t is 1.796. Now, one feature here is, what if this problem had stated the area to the left of t is 0.05? Okay, if you're talking to the left of t, you got to realize it's symmetric. So if the area to the left of t is 0.05, the area to the right is 0.05. So we would do the same thing. But since we're talking area to the left being very small, our t-value would be a negative. So we're going to use one table, and then we have to decide whether the t-value is positive or negative by where it's located according to 0. Okay, another example. Find t-value if the area to the right of t is 0.15, n is 7. So degrees of freedom, 7 minus 1 is 6. Call up the table. Find the area to the right, 0.15. Degrees of freedom, 6. Where that row and that column meet gives you your answer, 1.134 for t. So that's your t-value. This is how we use the student's t-distribution to find t-values. Now, the margin of error E in a 1 minus alpha times 100% confidence interval for a population mean is given by E equals t sub alpha divided by 2 times s divided by the square root of n, where t sub alpha divided by 2 is known as the critical value for the confidence interval. S is the standard deviation of the sample, and n is the sample size. Finding the critical t-value, t of alpha divided by 2, for a given level of confidence. Find t sub alpha divided by 2 if the level of confidence is 95%, n is 10. So in this case, alpha is going to be 0.05. So t sub alpha divided by 2 is t 0.05 divided by 2, which is t 0.025. Now from earlier chapters, if you had a z alpha sub alpha divided by t, 2, that value there in the subscript is equal to the area to the right. So t sub 0.025 means the area to the right of t is 0.025. N is 10. So degrees of freedom would be 10 minus 1, 9. Go to the table. We find 0.025 for the area in the right. There's the area in the right. Degrees of freedom, 9. Where this row and this column meet gives you your answer. So in this case, t would be 2.262. That would be your critical value for this problem. Now, what about when the level of confidence is 99%, n is 5? Well, alpha is going to be 0.01. T sub alpha divided by 2 turns out to be t sub 0.005. So the area to the right of t is 0.005. Degrees of freedom, 5 minus 1 is 4. Go to the table, find 0.005 for the area to the right, find 4 for degrees of freedom. Where that row, that column meet, this would be your t value, 4.604. Okay, and that's how we use the t distribution, or the student's t distribution. All right, a confidence interval is usually listed in one of 3 ways, just like we did for the proportion, except for now instead of p hat, we're using x bar. So it's x bar plus or minus e. Now remember, x bar is a mean, so it's going to be some number plus or minus numbers, like 123 plus or minus 25. Algebraic notation, mu is the mean of a population, so mu is going to be greater than x bar minus e, less than x bar plus e. So this would be 123 minus 25, 123 plus 25, or mu is greater than 98, less than 148. Interval notation, same idea, except for instead of p hat, we're using x bar. So it's x bar minus e, x bar plus e. So it's 123 minus 25, 123 plus 25, 98, comma 148. So x bar minus e is known as the lower bound, x bar plus e is known as the upper bound. Same as now, finding the margin of error and confidence interval by hand when x bar, s, n, and the level of confidence is given. Well, s already showed up early. Okay, so the recent survey asked 40 Americans during the past year about how many books, either hardcover or paperback, did you read either all or part of the way through. Results of the survey indicated that X bar was 13.4 books and S was 16.6 books. Construct a 99% confidence interval for the number of books that Americans read through either all or part of during the past year. So N is 40, that's the sample size. X bar is 13.4, and S, which was already showing up early, is 16.6. Level of confidence, 99%. So alpha is 0.01. So T of alpha divided by 2 is T of 0.005. We go to the table, we look it up, you get 2.708. Now, we take the formula. E equals T sub alpha divided by 2 times S divided by the square root of N. So we get 2.708 times 16.6 divided by the square root of 40. Use your calculator, you should get 7.107666176, and we round that off to 2 decimal places, let's say 7.11. So now we have our point estimate, which is X bar, 13.4, and now we have E, which is 7.11. So the interval is going to be X bar minus E, X bar plus E. So you take 13.4 minus 7.11, you get 6.29. You take 13.4 plus 7.14, you get 20.51. Okay, so hence mu is greater than 6.29, less than 20.51. And of course I forgot the degrees of freedom earlier. Now that's coming in late. S came in early, degrees of freedom come in late. Okay, finding x bar and e when given a confidence interval. Well, what's the interval x bar minus e, x bar plus e mean? Pretty much the same thing as what it meant for p hat minus e, p hat plus e. X bar is in the center, x bar minus e is the lower bound, x bar plus e is the upper bound. So x bar is the average of the lower and upper bounds, or x bar is lower bound plus upper bound divided by 2. E is half the distance from lower bound to upper bound. Because you're going from x bar down e, you're going x bar up e. So the difference between the lower and the upper bound divided by 2 would give you e. So you take the upper bound minus the lower bound divided by 2, that gives you your estimate of error, e. Okay, using StatCrunch to find a confidence interval for estimating a population mean. Well, in this case, you open StatCrunch, same way we always do it. This time you click Stat on the top menu. This time we're going to highlight T-Stats. Highlight one sample, click with summary or with data. Okay, with summary means you know the X bar and the S. With data means you just have a list of data. So you enter the value for the sample mean, which is X bar. You enter value for the sample standard deviation, which is S. You enter a value for the sample size, which is N. You click the circle beside confidence interval for P. It should be for mu. Another mistake. Enter level. Level of confidence as a decimal. Click compute. Now, same problem as before, and again, S is coming in early. And we get N, we have X bar, we have S, we have level of confidence. This time, that's all we really need. So now, if I opened up the one sample T summary, I would enter the sample mean, 13.4, the sample standard deviation, 16.6, 40 for the sample size, click confidence interval for mu, enter the 99%, click compute. And this is what I would get out. So in this case, X bar would be your sample mean, 13.4, but we already knew that. Then our interval would be lower limit, upper limit. So we have 6.29, 20.51 when we round off. And you notice we get exactly the same answer here as we got when we worked it by hand. And I think you'll see StatCrunch is a lot easier and a lot quicker. So mu is trapped between 6.29 and 20.51. Now, let me go to StatCrunch and run through this problem. So you would click Stat, highlight T-Stats, highlight one sample with summary. We're going to put the sample mean in, which was 13.4. The sample standard deviation, 16.6. The sample size was 40. We're going to click the confidence interval, and this time it was 99%. So I click 99 and click compute. And you notice I get the output, 13.4 here for the sample mean. The lower limit, 6.29 rounded off, 20.51 rounded off. So we get exactly what I showed you earlier, but that's how you would run through it in StatCrunch. Now, what about finding the sample size needed to estimate a population mean within a specific margin of error? Well, the sample size required to estimate the population mean mu with a level of confidence 1 minus alpha times 100% within a specific margin of error E is given by N equals the critical value of Z times S divided by E. Now, up to this point, we're doing everything with T values. Now we're going to use the critical value of Z times S divided by E quantity squared. So, example, a recent Gallup poll asked Americans during the past year about how many books, either hardcover or paperback, did you read either all or part of the way through? Initial survey results indicated that S was 16.6 books. So, how many subjects are needed to estimate the mean number of books Americans read during the previous year within 4 books with 90% confidence? Okay. So, S is 16.6. E is 4 because we want to be within 4 books. 90% implies the critical z-value is 1.645. Again, you can go to your standard normal table at the bottom and find the critical value for 90%. Okay, or 90% implies alpha 0.10, so the critical z-value would be 0.05. Now you could go in, use your normal calculator, enter 0 for the mean, 1 for the standard deviation, choose greater than or equal to, and then put 0.05 for the answer, click, and they'll give you the z-value of 1.645 when you round it off. All right, the formula for the sample size is n, critical z-value times s divided by e, quantity squared. So we substitute in. We get 1.645 times 16.6 divided by 4, quantity squared. When I go through this, I get 46.6045, so you might want to run it through your calculator, make sure you get the same answer, which would round up to 47, because remember, we always round up. So this would be how you would find the sample size needed. And unlike proportion, there is only one formula here. So now, what if I had the same problem? Okay. This time, I'm looking for a 99% confidence interval. Okay. So S is still 16.6, E is still 4. 99% implies the critical value is 2.575. And again, you can get that from the bottom of the standard normal distribution table, or you can plug in the normal use the normal calculator with 0.005 being the area to the right. The formula, N is critical z-value times S divided by E, quantity squared. So it's 2.575 times 16.6, quantity squared, divided by 4, quantity squared, which you could run through your calculator. You would get this answer, which rounds up to 115. Now, you notice what we had talked about in section 9.1. In this case, I increased my level of confidence. Okay? As I increased my level of confidence, what happened to the margin of error? The margin of error got greater, which means the interval got larger. And this brings you to the end.